Hello, welcome back. Wherever you are tonight, and I hope it is somewhere that has at the very least a degree of softness to it, some quality of chosenness, a sense that you have arrived rather than merely stopped, I am very glad you're here. Maybe it is the usual place, that particular corner of your night that has become reliable. Maybe it is somewhere new, a room you are still learning, a ceiling you have not yet memorized. Both are fine, both work. Go ahead and get comfortable. Not the provisional comfortable of someone still holding themselves slightly ready, the full, deliberate settling of a person who has decided where they are. Let your body take the weight back from the day. Let your shoulders drop. Let your jaw unclench. Breathe in. Breathe out. The words will come in slowly, at whatever pace serves you tonight. If you drift before we reach the end, that is not a failure of attention. That is the whole point. You don't need to retain anything specific. Nothing we discuss tonight will be on a test. Some of it may stay with you, the way certain thoughts do, not as facts but as textures. As a particular feeling that attaches itself to the way you look at a night sky, or notice the weight of a ring on your finger, or think, for a moment, about how old things actually are. If you're finding this place for the first time, welcome. This is Late Space. We take enormous things and hold them gently, at the speed the hour requires. If you'd like to come back on other nights like this one, a quiet like or subscribe helps other people who need somewhere to be at this hour find their way here too. But that is for later. Right now, just breathe. Tonight we are going to talk about the search for another Earth. Not in the abstract way that this phrase is sometimes used, not as a metaphor for hope, or a rhetorical gesture toward the possibility of life elsewhere, or a vague reference to the ambitions of space exploration. We're going to talk about it in the specific, precise observational sense, the actual search, the actual candidates, the actual light that has been collected by an actual telescope in actual orbit around the actual sun, and what that light is starting to suggest about whether rocky, possibly watery, possibly atmospheric worlds exist in places other than this one. And woven through that search is something that arrived when scientists looked more carefully at one particular planet, an ancient rocky world 10 billion years old, circling one of the oldest stars in our galaxy, and found something that should not have been there. An atmosphere. On a world that had roasted for so long, that had been so close to its star for so long, that the conventional wisdom said nothing could possibly remain. And that finding pulls at a thread that, once pulled, changes the question we've been asking. Not just, is there another Earth? But, were we the first? Is our civilization, our planet, our 4.5 billion year story actually early in the cosmic timeline of planetary life? Or have there been other Earths, older Earths, earlier Earths, worlds that had billions of years of head start on the chemistry that eventually produced something like us? Those questions don't have confirmed answers. Not yet, but they have, for the first time in human history, observational evidence underneath them. We are no longer asking them purely in the dark. We have data. Imperfect, incomplete, contested data, but data. Light from other worlds, filtered through instruments we built, telling us things we did not know before. Let's take it slowly. Let's start at the beginning. Close your eyes when you want to. We'll get there together. We should begin with the moment the universe decided to make planets. Not our planet specifically, and not the moment of our formation 45 billion years ago, but the moment the universe first had the ingredients to build rocky worlds at all. In the very early universe, in the first billion years or so after the Big Bang, the cosmos was made of a comparatively simple set of materials. Hydrogen, mostly, helium in smaller quantities, traces of lithium. That was it. No carbon, no oxygen, no iron, no silicon, no calcium, none of the heavier elements that make up the bulk of rocky planets. Those heavier elements didn't exist yet. They had to be made. They were made inside stars. In the nuclear furnaces of the first generation of stars, enormous, short-lived objects far more massive than anything that commonly forms today, hydrogen was fused into helium, and helium into carbon, and carbon into oxygen and neon, and magnesium and silicon, and in the most massive stars, all the way up to iron. And then those stars died, explosively, in supernovae that scattered their ash across space. The heavy elements they had forged in their cores were suddenly available, distributed into the interstellar medium, mingling with the hydrogen and helium that had always been there, slowly enriching the galactic reservoir of material from which future stars and planets might form. This process took time, not because stellar evolution is slow. The most massive stars live only millions of years, a geological eye blink, but because the abundance of heavy elements in the galaxy accumulated gradually, stellar generation after stellar generation, each cycle of star formation and stellar death, adding a little more iron, a little more carbon, a little more silicon to the available inventory. In the very early galaxy, in the first few billion years, the supply of heavy elements was thin. There simply hadn't been enough cycles of stellar birth and death to enrich the medium to the levels we have today. Stars that formed early formed from metal-poor material, in the astronomers' terminology, material with fewer elements beyond hydrogen and helium. The planets that formed around those early stars, if they formed at all, were correspondingly depleted in heavy elements. And yet they formed. This is one of the things that still surprises planetary scientists when they sit with it fully. Rocky planets require heavy elements, iron for cores, silicon for mantles, oxygen for rocks and for potential water. In the early galaxy, those elements were scarce. The expectation, for a long time, was that rocky planet formation would be rare in the early universe, limited to regions and times when the heavy element abundance had reached a threshold. That expectation has been revised, and the planet that revised it, more than almost any other, is a world called TOI 561b. TOI 561b was first detected in 2021 by NASA's Transiting Exoplanet Survey satellite, TESS, a spacecraft launched in 2018 specifically to look for planets crossing in front of nearby stars. TESS monitors the brightness of hundreds of thousands of stars, looking for the tiny repeating dimming events that indicate a planet has passed between the star and the telescope. The dimming is minute, typically less than 1%, but TESS's instruments are sensitive enough to detect it reliably, and the sheer number of stars it monitors means that even rare or unexpected planets have a chance of being found. TOI 561b was flagged as one of 3 planets around the star TOI 561, TESS Object of Interest 561, in the constellation Sextans, about 280 light-years from Earth. The star itself caught astronomers' attention not just because it had planets, but because of what kind of star it was. TOI 561 belongs to a population called the Galactic Thick Disk. This needs some explanation, because it's one of those astronomical details that sounds structural and turns out to be deeply historical. Our galaxy, the Milky Way, is not a uniform collection of stars. It has a thin disk, where most of the galaxy's current star formation happens and where our own sun lives, a relatively young, chemically enriched region, full of gas and dust and the heavy elements accumulated over many billions of years of stellar cycling. But it also has a thick disk, an older, more diffuse component sitting above and below the thin disk, made up primarily of stars that formed long before our Sun, in an era when the galaxy was young and its heavy element abundance was low. Stars in the thick disk are old, very old. They formed when the galaxy was in its early history, from material that had not yet been enriched to modern levels. TOI 561 is one of these thick disk stars. It is estimated to be approximately 10 billion years old. For comparison, our Sun is 4.6 billion years old, and the universe itself is 13.8 billion years old. TOI 561 formed when the universe was less than 4 billion years old. It has been burning for longer than our Sun has existed. And orbiting it, as TESS found in 2021, is a rocky planet. TOI 561b, a super-Earth, about 1.45 times the radius of our own planet and roughly 3 times the mass. Rocky, not gaseous, its density, measured by tracking the wobble it induces in the star through radial velocity observations, is consistent with a rocky composition similar to Earth's, one of the oldest rocky planets we have ever found. Lauren Weiss, who led the discovery team at the University of Hawaii, noted something that has stayed with me ever since I first encountered it. She said that the existence of TOE Y561b shows that the universe has been forming rocky planets almost since its inception. The universe was making worlds, dense, solid, rocky worlds, with cores and crusts and the basic architecture of a planet. 10 billion years ago, when the Milky Way was young, when the heavy elements were scarce, when everything we think of as the building materials of a solid planet was only available in depleted quantities. And if the universe was making rocky planets 10 billion years ago, then those planets have had 10 billion years of history since they formed. A head start on our own 5 billion year story of more than twice its length. Now here is where Webb enters the story, and where the truly unexpected thing was found. In March 2026, a team led by Johanna Teskey of the Carnegie Earth and Planets Lab in Washington, D.C., published results from Webb observations of TOE 561b. The aim was to characterize the planet's thermal emission, to measure how hot the day side of the planet was, which would tell them whether the planet had an atmosphere redistributing heat around it, or was simply a bare rock with the day side blazing and the night side cold. TOE 561b orbits its star in just 10.5 hours. Every 10.5 hours, it completes one full revolution. It orbits at roughly 1/40th the distance between Earth and the Sun. Far closer than Mercury orbits our own star. At that distance, the surface temperature of a bare rock would be approximately 2700 degrees Celsius, hot enough to melt iron, hot enough to keep large regions of the surface as liquid magma. A bare rock this close to its star should be blazingly, uniformly, searing hot on the day side. Webb observed the planet across 4 full orbits, capturing each moment when the planet passed behind its star, the secondary eclipse, when the planet's own thermal glow briefly disappeared and could be measured by its absence. The dayside temperature Webb measured was not 2,700 degrees. It was around 7,900 degrees Celsius. 1,000 degrees cooler than a bare rock would be. Something was redistributing the heat. Something was carrying energy from the blazing dayside toward the night side, moderating the dayside temperature below what it would be if the planet sat naked and unprotected in the light of its star. An atmosphere. On a planet orbiting in less than half a day, roasting at temperatures that should have stripped any gas away billions of years ago, an ancient 10-billion-year-old rocky world appeared to have a thick atmosphere. Not just a thin residual wisp. The deficit in dayside temperature was large enough to suggest something substantial, something actively moving heat around the globe. The team proposed that what Webb was seeing was a volcanic origin atmosphere, a secondary atmosphere, generated not from the primordial gas captured during the planet's formation, but from gases released by the planet's own interior, continuously replenished by volcanic outgassing as the magma ocean on the dayside interacted with the interior. In the researchers' own words, it was like a wet lava ball, the molten surface feeding gases into the atmosphere cycling around the planet, the interior continuously replenishing what the star's radiation stripped away, a dynamic equilibrium between destruction and renewal. The headline used the word impossible, a thick atmosphere on a world thought too extreme to hold on to any gas. And the word wasn't wrong. Exactly. Just premature. Not impossible, but unexpected. Not beyond the laws of physics, but beyond what the conventional picture had allowed for. TOE 561b is challenging something the community thought it understood, that ultra-short-period super-Earths are simply bare rocks, stripped of everything by the relentless proximity of their stars. That close to a star, for that long, nothing should be left. And yet something is. Wherever you are, I hope you're comfortable. Let's breathe here for a moment, because I want to make sure the philosophical weight of that finding has a chance to settle before we move on. TOI 561b is not habitable. Let's be completely clear about that. Its surface temperature of 1700 degrees Celsius makes it utterly inhospitable to any chemistry resembling life as we know it. It is not a second Earth in the sense of being a candidate for biology. It is a lava world, a molten, violent, ancient thing. But the question it raises is not does life exist on TOI 561b? The question it raises is what it tells us about the category of ancient rocky planets more broadly. If a 10-billion-year-old rocky planet orbiting this close to its star can maintain an atmosphere through continuous volcanic replenishment, what does that tell us about the range of conditions under which rocky planet atmospheres can persist? If worlds can hold on to gas under conditions this extreme, what happens on worlds that aren't this extreme? What happens on ancient rocky planets orbiting at habitable distances, farther from their stars, where the radiation is gentler and the temperature is cooler? The answer the scientific community has been building toward, not just from TOI 561b, but from a whole wave of Webb exoplanet observations, is that rocky planets are more geologically active, more chemically dynamic, more persistent in their atmospheres than the earlier, simpler models suggested. The universe makes rocky planets that endure, and some of those enduring rocky planets have been enduring for a very, very long time. If rocky planets have been forming for 10 billion years, and if some of them maintain the conditions for complex chemistry for long periods, then the question are, we the first becomes not philosophical, but observational. We can, in principle, look for evidence of what older worlds are like. We can study them. We can measure their atmospheres. We can look for signs of what 10 billion years of planetary evolution might produce. We're not there yet. But the tools are coming online. And what they're finding is not discouraging. Let me tell you about TRAPPIST-1, because it's impossible to talk about the search for another Earth in 2025 and 2026 without talking about TRAPPIST-1, the system that has occupied more of the exoplanet science community's attention than perhaps any other single discovery in the last decade. In February 2017, a team led by Michel Guillon at the University of Liege announced the discovery of 7 Earth-sized planets orbiting a red dwarf star about 41 light-years from Earth. 7 planets, all roughly the size of our own world, all orbiting in a tight configuration around a dim, cool, ancient star called TRAPPIST-1. 3 of those 7 planets orbit in the habitable zone, the range of distances from the star where temperatures might allow liquid water to exist on a rocky surface. Not definitely. Not without an atmosphere to maintain the temperature and pressure, but potentially. Given the right conditions, given the right atmospheric composition, 3 Earth-sized worlds around this nearby star might have surfaces on which water could remain liquid. The announcement caused a reaction in the scientific community and the public that is rare in astronomical discoveries. Not just interest, something closer to recognition. A feeling of arrival, of having found the specific kind of place that the search had always been aimed at. Earth-sized planets. Habitable zone. Nearby enough to study with existing and upcoming telescopes. TRAPPIST-1 was named for the Transiting Planets and Planetesimals Small Telescope in Chile, the facility used to discover it. The star itself is an ultra-cool red dwarf, smaller, cooler and dimmer than almost any other type of star, with a mass only about 8% that of the Sun. It glows in the infrared rather than the warm yellow-white of our own star, and the light that reaches its planets, even in the habitable zone, has a very different character than the sunlight Earth receives. Redder. More energetic in certain wavelengths, less in others. The star is old. Estimates vary, but TRAPPIST-1 is thought to be somewhere between 7 and 12 billion years old. Older than the Sun, possibly much older. If its planets have been in something like their current configuration for a significant fraction of that time, they have had billions of years of history that we are only now beginning to learn about. Webb has been observing the TRAPPIST-1 system since its science operations began in 2022. not continuously. Observing time on Webb is enormously competitive, with far more proposals submitted each cycle than hours available, but systematically working through the planets one by one, starting with the innermost worlds and gradually building a picture of the system. The results have come in slowly, carefully, with the patience that the questions demand and the uncertainty that honest science acknowledges. TRAPPIST-1b and TRAPPIST-1c, the two innermost planets too close to the star to be in the habitable zone, have both been measured via secondary eclipse, the same technique used for TOI 561b. For both, the dayside temperatures suggest little or no significant atmosphere. The temperatures are consistent with bare rock absorbing and re-radiating the star's heat directly. No redistribution, no greenhouse warming. These inner worlds appear to be airless, or nearly so, stripped by the proximity and the stellar radiation. This was disappointing to some, but it provided valuable information. The boundary conditions of the system were being established. The inner worlds could be characterized, and the habitable zone planets were still waiting to be examined more carefully. In September 2025, the first results from Webb observations of TRAPPIST-1, the fourth planet, one of the three in the habitable zone, the one most often cited as the system's best candidate for habitability, were published in the astrophysical journal Letters. The team was led by Instor Espinosa of the Space Telescope Science Institute in Baltimore and Natalie Allen of Johns Hopkins University, as part of a large international program called Dresst's Dreams, a name that manages to be both scientifically accurate and quietly poetic. What they reported was this: tentative evidence from 4 transits observed between 2023 and the time of publication that TRAPPIST-1 might have an atmosphere. Not a confirmation, not a detection at the level of certainty that would allow the word discovery to be used, but something more than nothing. The data did not match the expected pattern for a bare rock. There were deviations, subtle features in the transmitted starlight that were more consistent with some kind of atmosphere being present than with its absence. They also reported what kind of atmosphere it probably wasn't. A thick hydrogen-rich primordial atmosphere, the kind that forms from the gas a young planet captures during formation and before the star's radiation burns it away, was ruled out. If there's an atmosphere on TRAPPIST-1, it's something different. A secondary atmosphere, built up over time through geological processes, volcanic outgassing, chemical reactions between the rocky surface and any water present, the kind of atmosphere that Earth's own atmosphere largely is, rebuilt from the planet's interior after the primordial gas was lost. A secondary atmosphere that might sustain oceans, or ice, or both. The team was careful, as scientists dealing with marginal detections on the instrument's limits always need to be. Sukrit Ranjan of the University of Arizona, in a companion paper, urged specific caution about one feature, a possible methane signal that might be atmospheric in origin, but might equally be noise from the star itself. More observations were needed. 15 additional transits were already scheduled for late 2025 and into 2026. The picture would clarify. What the team described themselves as seeing was possibility, not certainty. A set of measurements that, for the first time, placed the question of TRAPPIST-1's atmosphere within the realm of things that a specific instrument could specifically address, rather than within the realm of things that could only be wondered about. Instor Espinosa, reflecting on what they'd found, said something that I keep returning to. He said that Webb's infrared instruments were giving them more detail than they had ever had access to before, and that the initial observations were showing them what they would have to work with when the rest of the data came in. What you will have to work with. That phrase carries in it the whole shape of what it is to be a scientist at a frontier. Not certainty, not answers. Tools and the knowledge of what more you can ask with them. Let me tell you about the star that TRAPPIST-1 orbits, because the star is as important to the story of habitability as the planet itself. In some ways, it's the central character. TRAPPIST-1 is an ultra-cool red dwarf of the type designated M8, near the bottom of the stellar spectral sequence, barely large enough to sustain hydrogen fusion in its core. It is about 12% of the Sun's diameter and has a surface temperature of roughly 2,550 Kelvin, compared to the Sun's 5,778 Kelvin. The light it emits is overwhelmingly in the red and infrared. The peak of its emission spectrum lies at wavelengths that are invisible to human eyes. Red dwarfs of this type are the most common stars in the galaxy. Something like 70 to 75% of all stars in the Milky Way are M-type dwarfs. If planets in the habitable zones of red dwarfs are broadly habitable, then most of the habitable real estate in the galaxy is orbiting red dwarfs, not Sun-like stars, the comparatively rare bright yellow-white stars like our own Sun. The quiet, dim, ubiquitous red dwarfs. Red dwarfs are old relative to more massive stars. They burn their fuel so slowly that they have lifetimes of tens to hundreds of billions of years, far longer than the current age of the universe. TRAPPIST-1 has barely begun its main sequence life. In its tenure as a hydrogen-burning star, it has barely covered a fraction of the time it will eventually spend. The planets around it, if they maintain the conditions for life, have more time ahead of them than behind. But red dwarfs are also, particularly in their youth, energetically violent. They flare frequently and intensely, emitting bursts of ultraviolet and X-ray radiation that can strip atmospheres and sterilize surfaces. Young red dwarfs go through periods of high activity that last billions of years, far longer than the brief energetic youth of more massive stars. TRAPPIST-1 was more active in the past than it is today, and its habitable zone planets endured that activity for billions of years before the star settled into its current relative quiet. Whether atmospheres can survive that bombardment, whether geological processes can replenish what is stripped away, whether the specific radiation environment of a red dwarf system can be compatible with the chemistry of life, these are genuine open questions. They are among the most important questions in astrobiology, and TRAPPIST-1 is the system in which Webb is best positioned to explore them. The fact that TRAPPIST-1 shows even tentative signs of something atmospheric, after surviving billions of years around a star that has been actively trying to strip its atmosphere away, is not nothing. It is evidence that at least some red dwarf planets can hold on to something, some protective layer, some consequence of their interiors that partially offsets the damage from above. It is evidence that the question of red dwarf habitability is not already closed. Wherever you are, I hope you're comfortable. We're past the midpoint now. The science is laid out. What follows goes deeper into the meaning underneath it. Let me bring the threads together. TOI 561b, the ancient rocky planet showing an impossible atmosphere from a world 10 billion years old. TRAPPIST-1, the Earth-sized habitable zone world showing tentative hints of something atmospheric, orbiting a star that has been burning for perhaps 7 to 12 billion years. And the larger question they share. If rocky planets have been forming since the universe was young, and TOI 561b is evidence that they have, and if some of those ancient rocky planets can maintain atmospheres under conditions previously considered too extreme, and TOI 561b's apparent thick atmosphere is evidence of that too, then we have to take seriously a possibility that the SETI pioneers of the 20th century raised in theoretical terms, but that the data is now starting to address in observational ones. We might not be the first, not in the tabloid sense of that phrase, not as a claim of contact, or detection, or even confirmed biology anywhere else, but in the deeper, statistical, cosmological sense. The universe has been making the conditions for something like life, rocky planets, stable orbits, persistent atmospheres, long timescales, for far longer than it has been making them here. Whatever process produced life on Earth, which required a rocky planet with an atmosphere and liquid water and around 4 billion years of chemistry to develop complexity, could in principle have operated on older worlds, around older stars, with more time. Whether it did is entirely unknown. But the question is not hypothetical anymore. It has a physical address. Let me tell you something about timescales that I find impossible to fully hold but impossible not to sit with. Life on Earth is old, by human standards. The oldest confirmed fossils of microbial life are about 3.5 billion years old. Complex multicellular life only appears in the fossil record about 600 million years ago. Vertebrates appeared about 500 million years ago. Our lineage, the hominins, diverged from other great apes about 5 to 7 million years ago. Homo sapiens, our species specifically, has been around for about 300,000 years. Written human history is perhaps 5,000 years old. The technological civilization that built the James Webb Space Telescope is about 300 years old in its modern form. 300 years out of 4.5 billion. Our technical civilization is about 1/15,000,000th of the age of our planet. TOI 561b's has existed for 10 billion years. More than twice the age of the Earth. More than twice the time it took for everything we know, the first cells, the Cambrian explosion, the dinosaurs, the mammals, the primates, the species that reads and writes and builds telescopes, to unfold on this planet. If something like life arose on TOI 561b, not on TOI 561b itself, which is too hot, but on some ancient rocky world orbiting at a more comfortable distance around one of the old stars of the galactic thick disk, and if it followed a developmental timeline even roughly similar to Earth's, it would have had twice as long to do it. Twice as long to go from chemistry to cells. From cells to complexity. From complexity to whatever comes after complexity. We don't know if that happened. We don't know if life is common or rare, if it requires specific conditions that are unusual or typical, if intelligence emerges reliably or is a bizarre accident. We don't know any of these things. But we know that the time was there. The stage was set. The raw materials were being assembled into rocky worlds, orbiting stable stars 10 billion years ago. And that fact, not the hypothesis, not the speculation, but the observationally confirmed physical fact that the universe was making rocky planets when it was still young, changes the nature of the question. Not is there life out there somewhere as an abstract philosophical wonder, but how long has the universe been capable of making the conditions for life? And if life tends to arise wherever those conditions are met, how long has it been doing so? I want to tell you about a specific scientist whose name belongs in this story, because she said something in connection with the discovery of TOI 561b that I find as elegant as anything I've encountered in reading about this subject. Lauren Weiss, the astronomer who led the discovery team, reflecting on the implications of finding one of the oldest rocky planets ever detected, asked out loud, what view of the night sky would have been accessible from a rocky planet during its 10 billion year history? The question sounds romantic, and it is, but it's also physically specific. The night sky from an ancient planet would have looked different from ours. The nearby stars would have been different stars. This was before our sun existed, before the solar system had formed, when the galaxy was younger and different regions were actively forming stars, and others had long since evolved past that phase. The density of the galactic disk, the distribution of star-forming regions, the background glow of a younger, more actively star-forming galaxy, all of it would have been different, visible from the surface of a world that has been orbiting its star for 10 billion years. And then, as the universe aged and other stars formed, and planetary systems coalesced around them, as the thin disk of the galaxy filled with younger stars like our sun, the sky from that ancient world would have slowly acquired new features. New neighbours. Eventually, about 4.6 billion years ago, the formation of a new star a few dozen light-years away, unremarkable in its own properties, but eventually, in the fullness of time, orbited by a small planet that would build a telescope and aim it back outward. The night sky is not static. It has a history. And if there are ancient worlds with skies to see through, those skies have watched the history of our neighbourhood unfold in ways we have barely begun to imagine. Let me be honest about the uncertainties in this story, because the uncertainties are real and they matter, and the honest version of the science includes them. The atmosphere on TRAPPIST-1 is not confirmed. The initial observations were 4 transits, enough to hint but not to establish. Follow-up observations have been undertaken, but as of this script. The full picture has not yet been published. One of the team's own collaborators urged caution about interpreting the hints as a signal rather than noise from the star. The data is marginal, and more is needed. The atmosphere on TOI 561b, the impossible thick atmosphere found by Webb, is the strongest result of the two, with a clear temperature deficit pointing to redistribution by something gaseous. But the nature of that atmosphere, its composition, its stability, the mechanism by which it is maintained, are still being worked out. The finding is real and the implications are significant, but it describes one specific lava world in one specific configuration, and extrapolating from it to conclusions about ancient rocky planets in habitable zones requires many steps of inference that haven't yet been observationally validated. The question of whether life exists anywhere else is entirely unanswered. All of the discoveries we've discussed tonight, the rocky planets, the atmosphere hints, the ancient worlds, are about conditions, not about occupancy. A planet with an atmosphere in a habitable zone around an old star is a place where the conditions might be compatible with life as we understand it. Whether life arose there, whether it persisted, whether it ever developed beyond the microbial, all of this is unknown, and not merely unknown in the we haven't checked yet sense, but unknown in the deeper we don't even know if the probability is high or low sense. The honest framing of tonight's topic is not Webb found another Earth. It's Webb is starting to show us what ancient rocky planets look like, and some of them are more complex and more capable of maintaining atmospheres than we expected, which expands the space of possibility for life in the universe without yet telling us whether that possibility has been realized. The frontier of science is not a place of clean answers. It's a place of carefully established new questions. Let me tell you about the Habitable Worlds Observatory, because the story of the search for another Earth doesn't end with Webb. Webb is the beginning of an era, not the whole era. The Habitable Worlds Observatory, WHO, is a space telescope currently in planning stages at NASA, intended to be the next flagship observatory after Webb. Its primary scientific goal is one of the most specific and ambitious ever written into a mission concept: the direct imaging and spectroscopic characterization of Earth like planets around Sun-like stars, specifically looking for signs of life. Not sub-Neptunes in the habitable zone of red dwarfs, which is what Webb is studying. Earth-sized rocky planets in the habitable zones of Sun-like stars, the most direct analogue to our own situation, the configuration most likely to produce an environment we'd recognize as Earth like in the fullest sense. Direct imaging of these planets, actually taking a picture of the planet's light, separated from the overwhelming glare of its star, is enormously difficult. The star outshines the planet by roughly 10 billion times in visible light. Separating the planet's faint glow from the star's blinding light requires a coronagraph of extraordinary precision, combined with a mirror large enough to provide the angular resolution to distinguish the two. WHO is designed around exactly this challenge. It would be capable of detecting oxygen in the atmosphere of an Earth analogue, of measuring water vapour, of looking for the combination of oxygen and methane, two gases that react with each other and can only coexist if something is continuously producing them, most plausibly life, that would constitute the strongest possible atmospheric biosignature from a safe distance. WHO is not yet approved, not yet funded at the construction level, not yet a reality. It is a priority recommendation from the most recent decadal survey of astronomy and astrophysics, the document that guides NASA's large mission choices for the next decade, and its development is progressing through the stages that precede approval. The current estimates suggest it could launch sometime in the 2040s. The people who build it will likely not be the same people who are planning it today. Some of them are not yet in their careers, not yet in graduate school, possibly not yet in high school. The search for another Earth is a multi-generational project, as all the most important scientific projects have always been. There's something I want to say about the phrase "we're not the first" in the title of tonight's episode, because it's doing two different things at once, and both are worth naming. The first is the literal claim implied by the science, that the universe has been making rocky planets for 10 billion years, long before Earth formed, and that some of those ancient rocky worlds have the properties that on Earth allowed for the emergence of life. Whether any of them are or were inhabited is genuinely unknown. The "we're not the first" is speculative, a hypothesis, not a finding. But it is a hypothesis with more physical support underneath it than it has ever had before. The universe was making the conditions for something like life long before it made the conditions here. The second thing we're not the first is doing is something stranger and more personal. It's reaching for the particular quality of vertigo that comes from genuinely, viscerally absorbing that our planet is not the only one, that our history is not the only history, that the timeline of complexity and chemistry and perhaps of life extends back further than our own beginning, in directions we have barely started to look. Most of us, most of the time, live as if Earth is the only world. Not as a stated belief. Anyone who thinks about it for a moment knows intellectually that the universe contains other planets, but as a felt sense of reality, the practical assumption that underlies everyday life. The world is here, and we are in it, and it is what exists. Other worlds are abstract, distant, theoretical. The discoveries being made by Webb are slowly, incrementally, observationally making them less abstract. TRAPPIST-1 is 41 light-years away. 41 light-years, a number so large it might as well be infinite for any practical purpose. But it is a specific place, with a specific set of atmospheric measurements, with a specific set of constraints on what kind of world it might be. It is a real object, not a symbol or a possibility or a thought experiment. It is a place with latitude coordinates and an orbital period and a transit duration, a place that Webb has watched pass in front of its star and whose light has entered our detectors and been analysed and written up in papers published in the Astrophysical Journal. The universe is not becoming smaller, but our instruments are reaching further into it, and the things they're finding are becoming more particular, more specific, more real. Now let's go very slow. Let's bring this down toward the end of the night. Here is what we know, as clearly and honestly as I can state it. Rocky planets have been forming in our galaxy for at least 10 billion years. TOI 561b, a world roughly 45 times the size of Earth orbiting a thick disk star 280 light-years away, is one of the oldest known rocky exoplanets, and in March 2026, Webb found evidence of a thick atmosphere around it, a result that challenges the assumption that worlds this close to their stars for this long cannot retain atmospheric envelopes. The mechanism appears to be volcanic replenishment, the planet's hot interior continuously feeding gas into an atmosphere that the star continuously strips away, a dynamic balance between interior activity and stellar erosion. 41 light-years away, in the TRAPPIST-1 system, a planet called TRAPPIST-1 orbits in the habitable zone of an ancient red dwarf star. It is Earth-sized. Its orbit places it at temperatures where, with the right atmosphere, liquid water could exist on its surface. In September 2025, Webb published the first observations suggesting that something atmospheric might be present, not confirmed. Not definitive, but more consistent with an atmosphere being there than not. More observations are underway, and the picture is still developing. Underneath both of these findings is a shift in how we understand the population of rocky planets in the galaxy. They are older, they are more numerous, they are more geologically active, and they are more capable of holding onto atmospheres than the earlier models suggested. The universe has been building the conditions that on Earth led to the emergence of life for longer than Earth has existed. Whether life arose elsewhere, whether it persists elsewhere, whether the complexity of chemistry that produces something like consciousness has happened anywhere other than here. All of that remains unknown, genuinely unknown, not as a rhetorical gesture, but as an honest statement of where the evidence currently stands. But for the first time in the history of our species, we are asking these questions with instruments capable of detecting the answers. Not imagining, not theorizing. Measuring light from other worlds, filtered through their atmospheres, reaching our telescope, telling us what molecules are there, how warm it is, whether something might be breathing or dissolving or cycling through the seasons. The answers are not yet here, but the tools are. Before I let you go, I want to offer you a specific image to carry with you into sleep. Not a metaphor, an actual physical image. In January 2026, NASA published Webb's observations of TRAPPIST-1 as a data graphic, a comparison of spectra from the planet's transits against theoretical models, one showing what the data would look like if there were no atmosphere, and one showing what it would look like with various atmospheric scenarios. The two curves are different. The data doesn't obviously align with either, which is itself informative. It suggests neither the simplest bare rock scenario nor the simplest thick carbon dioxide scenario, pointing towards something more nuanced, something in between or different in kind. The graphic is not dramatic. It is a plot with error bars and model lines, the visual vocabulary of a scientific paper, not of a headline. But what it represents is this: light from a world 41 light-years away that has been orbiting its star for possibly 7 to 12 billion years, filtered through whatever thin layer of gas might exist between the surface and the vacuum, has travelled across that distance and entered a mirror that humans built and launched into space, been sorted by wavelength, quantified, transmitted to Earth, processed through software, compared against physical models of how different atmospheres would interact with different wavelengths, and the result is a graph that says, we don't know exactly what's there, but it's more interesting than nothing. That graph is one of the most remarkable documents our species has ever produced. Not because of what it proves, because of what it asks. Close your eyes if they're not already closed. Somewhere in the direction of the constellation Aquarius, too faint to see with the naked eye, 41 light-years away, a small rocky planet is circling a dim red star. It has been doing this for billions of years. Whatever conditions exist on its surface, whatever chemistry has proceeded there, whatever the answer turns out to be when we finally have the measurements to read it clearly, all of it has been happening for a very long time without anyone on this particular blue planet knowing it existed. We found it 12 years ago, and we're still learning what it is. And 280 light-years away, in the direction of a faint southern constellation called Sextans, a lava world is orbiting a 10-billion-year-old star in less than half a day, its molten surface feeding an atmosphere that has been cycling in and out of existence for longer than our sun has burned. A world that should, by the old models, be bare rock, but isn't. A world that has been doing something unexpected, quietly, for most of the history of the galaxy. And somewhere in the space between these known worlds and all the unknown ones, the billions of planetary systems in the Milky Way that we have not yet looked at, that no telescope has yet targeted, that exist in complete indifference to our observations. Some fraction of them, perhaps, are rocky, and some fraction of those are old, and some fraction of those are in habitable zones, and some fraction of those have atmospheres, and some fraction of those might have something living in them. We don't know. We are still learning. But for the first time, we are learning from light. Real light from real worlds, collected by a real instrument, interpreted by real people who have devoted their careers to asking the most important question that a technological civilization can ask. Are we alone? The answer is still uncertain, but the question has never been better asked. Thank you for spending tonight here. Thank you for lying still and letting these ideas come in slowly, at the pace the night allows. Thank you for being the kind of person who finds 10-billion-year-old planets worth staying awake for, at least for a little while. The search continues, the instruments keep watching, the data keeps coming in, and somewhere in it, maybe soon, maybe not yet, maybe in a form we haven't learned to read, there might be an answer. Sleep well. And 41 light-years away, in the direction of a star too dim to see, a small planet is crossing in front of its sun, leaving a faint mark in the light. We're watching. Good night.